I'm Madeline James, and welcome to part 4 of this world building guide series. I'll include the video to go back and watch the first part of this series if you haven't already. These videos do kind of build upon each other, so you can't really jump into part 4 if you haven't also gone through parts 1, 2, and 3. But anyway, so at this point, we have our elevation maps, we have our physiographic regions, we have our land masses, etc. And now our next step is to map air currents and circulation and high and low pressure regions. You may be asking, why is this necessary? It seems really particular. That is because we need to map temperature, precipitation, and the seasonal differences between them. And the way to do that is to look at air and ocean circulation and pressure zones. I feel like I start every video like this, but having your elevation map and having the forms of your land masses, you can find quick guides to just take those, immediately go to your climate zones just based off patterns that you see on Earth. But again, then why are you here? Let's move on. And if you are wondering, is air and ocean circulation and all this stuff really necessary for figuring out temperature, precipitation, and all that stuff? Yes it is. I will sort of apologize in advance though. I would love to go significantly deeper into this topic, and this video is already going to be a good amount of lessons on air and ocean circulation. These things are incredibly complicated, and just to understand them well enough to apply them as much as we're going to is going to take some thinking. But I'm not a meteorologist, so we're not going to go super duper deep into this, and I do think that's sort of a level that I don't think is going to be necessary here, but if you find this interesting, I encourage you to research it and look into it more, because it's always fun and you can find ways to apply it to your maps. We're going to start with a lesson on atmospheric circulation. Atmospheric circulation describes the large-scale movement of air around the globe. It varies throughout the year with annual cycles, like seasons, and longer-term cycles, but for the most part, it's relatively constant. This movement of air, combined with ocean circulation, are the major forces that distribute heat throughout the planet. Planets have wind and pressure belts that wrap around them, and this will basically be the same for every single Earth-like planet, since they are determined by things like planet size and tilt. Alright, so let's pretend this is actually a circle and looks like a globe. But anyway, so you're going to have the Intertropical Convergence Zone, or ITCZ, along the equator. ITCZ, along the equator. The subtropic high belts are going to be at 30 degrees north and south. And then you're going to have your subpolar low belts at 60 degrees north and south. So your ITCZ, this is also called your doldrums. And the winds at the subtropic high belts are also called your horse latitudes. There's a kind of sad story there about ships being stuck in this wind belt and not moving and having to toss the horses overboard. And then the winds at your subpolar low belts are sometimes called your polar front. In between these belts, you get 6 major circulation cells, so 1, 2, 3, 4, 5, 6. Since hot air rises and the air at the doldrums is the hottest, you will have a lifting and spreading of that hot, moist air, and after rising, that air will travel away from the equator. It will cool off and sink at about 30 degrees, your horse latitudes, at the subtropic high wind belts. The winds then travel along the surface back to the equator, and then repeat the cycle. So it's sort of going up, out, down, like this, right? These cells will also be deflected towards the east or west based off the wind belts there between. This sort of movement happens between all the wind belts, and this creates your circulation cells. So from this we get our global surface winds. Let's use a different color. Let's use this blue color for this. So your trade winds, or your tropical easterlies, blow from 30 degrees towards the equator and from east to west. So in the northern hemisphere, these blow from the northeast, and in the southern hemisphere, they blow from the southeast. So these are going to kind of go like this. And again, these are called your trade winds or your tropical easterlies. Your prevailing westerlies blow from 30 degrees and towards 60 degrees from the west to east. So in the northern hemisphere, these blow from the southwest, and in the southern hemisphere, these blow from the northwest. So this is essentially going to look like this. These are our prevailing westerlies. The polar easterlies are going to blow from the poles to 60 degrees and from east to west. So in the northern hemisphere, these blow from the northeast. So essentially mimicking this sort of a look, going like here. And in the southern hemisphere, these blow from the southeast. So they essentially look like this, similar to the tropical easterlies. Again, they're both easterlies. So what are the implications of this? What does atmospheric circulation mean for temperature and precipitation? Hot air can hold more moisture than cold air. So as hot air rises and cools, it will precipitate. When cold air is falling, it's already lost a lot of its moisture and will be dry. This essentially means around the equator, it is going to be hot and wet, which basically means high precipitation. At 30 degrees north-south, it will be warm and dry, high evaporation. Around 60 degrees, it'll be cool and moist. And at the poles, it will be cold and dry. And this is a very high-level look of atmospheric circulation. So there are a few complications to this otherwise neat and tidy description of atmospheric circulation. Land masses and tilt. The ITCZ, or the Intertropical Convergence Zone, does not follow the equator. It follows the hottest part on the planet. The equator is roughly the hottest part of your globe, but depending on the season, this is not true. Since the Earth is tilted, depending on the season, you will see different parts of the globe actually being the hottest depending on the season. During the summer, in the northern hemisphere, you will see the Tropic of Cancer, essentially 23.5 degrees north, actually being the closest to the sun and therefore the hottest. And in summer during the southern hemisphere, you will see the Tropic of Capricorn, 23.5 degrees south, being the closest to the sun and the hottest. So due to this, the ITCZ will shift towards the north during the summer in that hemisphere and towards the south during that hemisphere's summer. But that's not the extent of this complication. Where do continents come in? Have you noticed that when you go to the beach, it takes the water sometimes until the end of summer for it to really warm up? This is because the ocean heats up a lot slower than land does. Due to this, there isn't as much time for the heating of oceans to change much seasonally. It does shift slightly, but the hottest part of the oceans really only goes between 10 degrees north and south. But since land heats up a lot faster, you will see these shifts a bit more drastic. Where there are large land masses around the latitudes that are closest to the sun during that season, the ITCZ will be pulled up even further. And this messes with the other belts as well because, again, they are all connected through these circulation cells. The subtropic high belts will be roughly 30 to 35 degrees north and south and closest to the pole in summer and closest to the equator in winter. The subtropic low belt is going to be significantly more complicated due to the polar vortex, and so we won't get into that too much right now. These belts will be roughly 60 to 70 degrees and will be mostly contained in uniform and the strongest in winter. Having this belt broken up by large landmasses will weaken the belt and make it a lot more likely for there to be waves and outbreaks. We will talk about this more in global weather patterns, but I do have an article linked below by Britannica that kind of describes this phenomena really well. But let's move on to mapping air circulation on our map. Alright, so I have out my updated landmasses map. I'm going to add the major latitudes onto this map so that I can make copies for my air circulation map. So I'm going to go do that real quick. Alright, so for prepping your air circulation maps, you're going to want to have two of these, both with seasonal air circulation on the top, just so you remember what these are, and then one map will have summer solstice in the northern hemisphere and winter solstice in the southern hemisphere. And then your other map will be the opposite. So winter solstice, northern hemisphere, summer solstice, southern hemisphere. Wow, I cannot say that. But these are essentially your January versus July maps. Alright, so I'm going to get out my little cheat sheet here again, which I folded up to draw these lines, so just ignore that. But then we are going to want to start with the summer solstice in the northern hemisphere, so this map here. And we're going to start by drawing our ITCZ. And because the ITCZ is wet, let's use blue for this, so I'll get out a blue color. And essentially, if you have any large air masses around 23.5 degrees north, which is going to be maybe around here-ish, the ITCZ will travel across the land around those latitudes. Otherwise, the ITCZ will follow the closest large land masses between the tropics, and if there are no large land masses, the ITCZ will travel around 5 degrees north, and you want to gradually connect these. So let's start with, so at 23.5, this is technically around 23.5, the bottom edge of this landmass, but that's not quite going to pull it up as much. It'll pull it up maybe a little bit more than 5 degrees, the slightest bit, but for the most part, we're going to be looking over here. So this is probably wide enough that the ITCZ will probably get up to this area. So we'll say it'll get up to like maybe there-ish. And over here, it's not quite as wide, so it is not going to go that far north. So we'll say maybe around here, there'll definitely be some sloping. And then around here, this is going to be around 5 degrees north, which we'll say, you know, here-ish. It'll move up slightly here, so we'll say here-ish. And here we'll be back down to here-ish. So we're just going to kind of connect these, and this water between here and here is not very wide, so it is going to dip down in between these two continents, but not all the way down to here. So let me connect all of this. Okay, so there is our ITCZ / doldrums, which is hot and wet. So now we're going to do the same thing on our other map. So I'm going to pull this map out, and we're going to be looking at the southern hemisphere. So this is basically around here. The only place where we really have land here is going to be over in this continent. So this is going to all be right around 5. And this will be closer to that 23.5 degrees south. And then over here, there's going to kind of maybe be a little bit of equal pulling here. So I'm going to have it maybe like right along the edge here. So, okay, so there's the ITCZ and the doldrums when they are in the southern hemisphere. So now we're going to move on to the subtropic high belt. Again, we're going to start with our map with the summer solstice at the top here. And these belts will be between roughly, let me get out this color, will be between roughly 30 and 35 degrees north or south. And they should be closer to the poles, 35 degrees in summer, and further from the poles in winter. And again, this is going to slightly be pushed depending on your ITCZ. So this is summer, right? So they're going to be a little bit closer to the poles, so closer to like maybe up here. So, and I will kind of push them a little bit further up here, but otherwise it'll be pretty constant. Okay? And then in the southern hemisphere, where it is winter, they will be a little bit further from the pole, so right at 30 degrees. And we'll just kind of basically do a quick, like, little band across. This is going to be your subtropic high. And this is going to be warm and dry. And we'll do the same thing on our other map. So where it is winter, this is essentially going to hug 30 degrees. So we'll just draw that right across here real quick. Okay, and then up here, it's going to push a little bit further towards the poles since this is summer. And especially in areas where the ITCZ hugs really close, we'll push it a little bit extra. Okay, so now we're going to draw our subpolar low belts in their most stable form. You'll remember there's a lot of variation in these belts, but essentially these are going to be between 60 and 70 degrees north and south, and will slightly stretch further south over large land masses when possible, more so in the summer hemisphere than in the winter ones when the winds are stronger. So we are in the summer hemisphere where the winds are not as strong, so between 60 and 70 when there's no large land masses, so not over here, not over here. So we'll go maybe around here. And then, let's see, we'll have it dip slightly here. And then go back up and maybe dip again here. Okay, and then in the winter hemisphere, the winds are pretty strong. So we're not going to have very much variability here. And this is our polar front, which is cool / moist. Okay, so then let's look here. And again, in the summer hemisphere, we will have a little bit more variability in these, which I'm gonna have this go, this is a pretty big landmass, right? So I'm gonna have this go all the way down to like here. And then come back up to about here. And then here, it's gonna be a lot more stable, probably not really any pull from these smaller continents. Okay, so that's essentially what we have, and one more thing to sort of help a little bit would be just to give an idea of your major wind cells. But essentially, your main wind circulation is going to follow this pattern here. So we're going to go from our subtropic high towards the ITCZ, moving in this direction. So, you know, we'll just draw a couple in here. I'm just going to draw this really lightly. Right, just like a little hint, just so that I remember which way these winds are blowing. I'm only going to draw this on one of these maps for now. I'll draw it on the other one eventually, but I'm not too worried. Now let's talk about high and low pressure. If you've watched the Weather Channel, they talk about high and low pressure systems moving around pretty frequently. As storms and other atmospheric events occur, they cause pressure changes. These aren't really things that we can map, but once we get to the kind of global weather scale, we'll be talking a lot about where you're going to see things like hurricanes and frequency of storms and all of that. But right now, we're going to be talking about semi-permanent pressure zones. At this point, we already know our major zones of high and low pressure. Around the equator / the ITCZ, we have about 10 degrees of low pressure. At the subtropic belt, we have 10 degrees of high pressure, and at the subpolar belt, we have 10 degrees of low pressure. However, in actuality, these high and low pressure zones are not actually belts, but more like cells. The only places on your globe that you will have sort of stable belts of pressure around the whole circumference of your globe is going to be if you just have continuous ocean. On Earth, for example, you will see a continuous band of low pressure at the southern hemisphere's subtropic low belt, since it travels mostly uninterrupted by continents. And then you will have a high pressure zone over Antarctica, where you have a continual landmass south of the subpolar belt. The northern hemisphere has a lot of continents and oceans all separated, so you'll see a lot of high and low pressure cells versus bands. As we talked about before, oceans hold on to heat longer than land does and takes longer to heat and cool, versus land, which heats up and cools really quickly. So large land masses and large oceans will have a big effect on low and high pressure zones. Okay, so to prep your maps for pressure, you're basically going to do the same thing as before, write pressure in the upper right, and then on one map you're going to have summer solstice in the northern hemisphere and winter solstice in the southern hemisphere, and then the opposite for the other map. These maps are going to mostly be based off of our seasonal air circulation map, so again the pressure is going to be seasonal because it's based off seasonal effects. Alright, so this blue color is going to be our low pressure color like it is over here with the ITCZ and the polar low belt. This kind of like yellowy orange brown color is going to be our high pressure color, just like the subtropic highs here and here. And we're going to use these to mark in the different pressure zones. I have all the maps laid out, so we have winter, summer, summer, winter lined up over here, so we can sort of reference this to actually draw in our pressure zones here. So step 1, we are going to mark high and low pressure bands where the wind belts flow uninterrupted by continents. So if you have one continent at a pole separated by ocean and the subpolar belt, this will be an area of high pressure. So on my map, The subtropic high belt here is mostly uninterrupted, but not entirely. I actually don't think I have any of these belts that are uninterrupted by consonants, right? Because like across here, consonant, consonant. Here, obviously, completely cut up apart. The ITCZ is cut up. The subtropic high belt here is probably the most uninterrupted. And even here, where it's a little bit lower, that's still going to be a little bit interrupted, although you do see your ITCZ also being mostly uninterrupted. But I won't have anything to map here, but essentially what you would have is a just single band of color where you have that uninterrupted belt. Step 2. We are going to add high or low pressure cells over large oceans where your wind belts are. These will obviously be high pressure cells for high pressure belts and low pressure cells for low pressure belts. These high pressure zones will be greater in winter hemispheres and low pressure zones will be greater in summer hemispheres. And if they are large enough, they should have extreme pressure areas around the center, relatively small comparatively. So let's start with where they will be greater. So let's start with high pressure zones in winter hemispheres. All right, so we have our high pressure color and we're looking at the winter hemispheres. So that's going to be up here and all the way down here. And so you will see that there's not a ton of water uninterrupted here. We have a lot of continent. So we're just going to start with kind of drawing a little bit here, a little bit here. And then down here we have a bit of a larger area. So this is going to be a lot more significant of an effect. So I'm just going to draw these in real quick and kind of make them a little bit more extreme because it's, the solstice where that hemisphere has a greater effect of this pressure. So. Okay, so then we're going to move on to the low pressure color and we're going to look at the summer hemisphere. So we are looking this summer hemisphere and this summer hemisphere for the low pressure bands. So I'm going to be drawing a pretty substantial effect right here because this is a large uninterrupted, swatch of ocean where the ITCZ is going to have a big effect on this. So we're really going to draw it out here and over here again. In this hemisphere we have a fairly large, not as large area, so this will be a big effect here, and then in this area here's, and a little bit here we'll also have some of this low pressure. So let me draw that in real quick. And you can see here that in some of these areas where I've drawn it in darker, that's like an extreme low pressure area. So we have extreme low pressure here where it's going to be a lot more of an extreme pressure effect. Here, a little bit here, and then I have the high pressure ones here and here. So then we're going to work on the smaller, less significant effects. So that'll be low pressure in winter solstice and high pressure during summer solstice. So let's move back up here, look at low pressure. Okay, so we're going to be looking at the low pressure up here for this polar low belt, and we're going to be down here, same thing, looking at this for this polar low belt. The ITCZ is in the other hemisphere at this time, so we only have to worry about this one belt. So I'm going to get that drawn in, and then for high pressure, we're going to be looking at the subtropic high down here in the summer hemisphere and the subtropic high here in this hemisphere. This one's not going to have a super big effect here. It's not a lot of area. It's a much smaller pressure effect, so this will be pretty minor. And then up here, you do have a bit of open area, so this will be a little bit bigger, but not super significant. And then for the low pressure zones up here for the polar low, relatively small, not super uninterrupted. And then down here, it's going to be really, really minor because this is all pretty separated. So I'm going to just draw these more minor effects in real quick. Okay, so that was step 2. So for step 3, In the colder or winter hemispheres on each map, we're going to extend our high pressure zones over large land masses, especially near your high pressure belt. And this would occur because the land is cooling faster than the oceans. If you have a lot of high pressure cells relatively close together, you might almost get a belt-like pressure belt. Okay, so I have my high pressure color. So we're going to be looking at the winter hemispheres and high pressure zones. And so I think that this isn't really going to extend over anywhere too significantly on this hemisphere because there's not a lot of land for it to extend over. I might just kind of draw this out because it would stretch over these little swatches, but it's not going to be very significant. And then over here, we are going to have this extend out over this one, here and here, especially this one right here. So let me draw these in real quick. Okay, so now for the low pressure zones, we are going to work on these in the continental areas in the summer hemispheres. And this is going to be happening because the land is heating faster than the oceans. And again, if you have a lot of those close together, they may join to get a belt-like pressure zone. You see this a lot in the northern hemisphere, around northern Africa and into Asia on Earth. So for my map, I'm going to be extending this. So for the equator, this is not going to have as significant of an effect. The equator, like as a low pressure zone, really isn't that significant. So I will see this like a little bit, maybe patching up in the middle of these equatorial continents, but it's really not going to make a band for the ITCZ. Sorry, I meant ITCZ, not equator. Our polar belts. Again, this is going to have a little bit more of an effect. We'll see a little bit more of a band cropping up here, and it'll cover up a little bit more over the oceans, or over the continents, but it's not going to be like super as significant of an effect. So I'm going to go through and just draw this in real quick. So something else that we are going to see here, and you can sort of see this on Earth, but we sort of have in the southern hemisphere a sort of polar continent that wraps around the pole. And something that you'll see on Earth is there is a little bit of a high pressure zone there to balance it out. So when we get to the step where we're balancing, we're probably going to have a little patch of high pressure right down here at the poles, just to kind of keep everything balanced. All right, so now that we have these sort of major effects in, we are going to add a bit of balance. So if you have a high pressure zone near another high pressure zone, you might either connect them or you might balance them out with a low pressure zone in between them, depending on what makes the most sense. So in here, like I mentioned, we're going to probably have a little bit of high pressure down here. And you see this on Earth with Antarctica too. Just to kind of add a little bit of that in there. And then we're probably going to see this kind of go up a little bit higher, be a little bit more extreme, sort of cut off these areas. And honestly, like this might even wrap up all the way through into here. And this is going to go up a lot too. These are going to be pretty minor in this hemisphere right there. And then down here we have a full belt, and it's balanced pretty well on either side by these low pressure zones, which is kind of what we want to see. I think this is probably, other than like extending this, I think this is probably pretty balanced. And then down here, and then up in this hemisphere, again, we don't have a lot of balance. There's a ton of this low pressure, and not a lot of this high pressure color. So what I would probably expect to see is that these are going to get a little bit more significant in these oceanic areas, whereas we're probably actually going to have our low pressure color, well, I think our low pressure color will see little patches in these continents. So I'm going to add little patches of low pressure here and kind of fill everything out a little bit, and then we'll see what it looks like when it's done. Okay, I think this is actually pretty good and balanced. Let me make sure you can see all this a little bit more, but everything kind of balances out in here and down here, and I think it's pretty good. Let's move on to mapping wind currents. We'll be referencing our pressure and air circulation maps to create these, and it's really just going to help us have an idea of which direction wind is moving, which is going to play a really big effect when we look at precipitation and temperature, because if you have wind blowing over a cold ocean versus hot land, that's going to cause different things, right? And the amount of humidity in that air. The first few times I world builded, I did not actually create a wind current map, and I sort of had to reference my maps as I was doing the temperature and precipitation ones to be like, okay, well, based off this, the air is moving this way, and it just got too complicated. Like, this is a very complicated process, but we kind of make all these little map steps along the way, both to allow us to just easily reference them and kind of move easily from one step to the next without it getting too complicated. Because if you're referencing like 13 different maps just to come up with one small thing in one small part of your map, that's overwhelming and is going to lead towards a lot of mistakes. The climate mapping is already going to be complicated enough because you are going to have to reference a lot of different things, so we just want to make everything as easy as possible until we get there. Okay, so mapping wind currents. I prepped 2 more maps, basically the same way. So wind currents, summer, winter, winter, summer. And then for my guide, or my key, I have onshore winds and offshore winds, which is going to be this color. And then I'm going to draw the actual wind currents in this brown color, just kind of to give this a different color than the ones we've been using, which have mostly been the same. So we're going to do one map at a time this time. So we'll start with summer. And so we're mostly going to be looking at the summer pressure map and then the seasonal air circulation map. In the northern hemisphere, a high pressure zone will have wind currents moving away in a clockwise direction, and in the southern hemisphere, they will be moving away in a counterclockwise direction. So in our winter hemisphere, where the high pressure zones are going to have wind currents going away counterclockwise, we are going to be looking at this area of high pressure here, which will be going right along through here, and so we want to add the wind currents moving away from them. So I'm just going to go through and kind of draw little arrows going away from this here in a counterclockwise direction. And then up here we have this area. I'm going to have them going the opposite way, leaving away from that. So let me do that real quick. So when you have low pressure, you will have wind blowing towards the center of the low pressure. And in the northern hemisphere, they will have a clockwise spin on them, while in the southern hemisphere, a counterclockwise spin. Okay, I think that's about that. Okay, so the next step is to pull in our air circulation maps and sort of fill in all the gaps with the way these belts would be moving. So you can see that this is a low pressure color, so they're sort of moving into this, and you'll see the opposite down here. And you will see that for the most part, some of these are moving in the same direction as you'd expect. So like low pressure in the northern hemisphere is moving in this direction, and you sort of see that moving into here. This is a very general map, so we'll just kind of do our best to sort of balance it out and make sure the wind current sort of makes sense. it's okay if this looks like a complete mess of arrows. We'll be looking at mainly the coastlines. So don't worry about it too much if this just looks like an utter mess. You don't need to make sense of these brown like wind lines right now. Alright, so I wanted to make this slightly clearer. So actually let me get a different color. So if we're looking at, you know, any of these maps really, we'll say this is the our seasonal air circulation winter summer. So this is my, let me make sure I say this right. This is my low pressure color. So low pressure color, obviously we have our ITCZ is a low pressure area, but the actual winds with low pressure, we're going to be looking at these winds here. So if I draw the winds like this, which I had these drawn, but they weren't kind of colored to make it super clear. But these winds right here, these are also called your westerlies because they blow from the west. So then you'll see that down here too, blowing in towards here. And again, these are westerlies. And then we will have, for high pressure, we're going to be having the winds blowing towards the ITCZ. So this is basically going to be blowing like this. And these are going to be the easterlies, or you can call them your trade winds. And they'll do the same thing, just kind of reverse from up here. They're blowing towards your ITCZ, your doldrums, still trade winds. And then also you're going to have this coming from the poles. So we'll see a little bit here and a little bit here. And these are essentially going to be your polar easterlies. So I hope this gives a slight better look at these winds and the direction that they're moving, so that you can apply those to the wind current maps to sort of fill in the gaps, because you know sort of which direction the general winds are going. But yes, okay, I'm going to get back to that. So for sort of filling this in, you don't need to have effect on every single shore, especially if there's not any significant like effects going on there. And looking up in here too, like I sort of know that the winds are blowing in this direction here, so I might add like carry that down here. This is going to move offshore here. This is going to be winds going in this direction, right? Like you can sort of like connect all of these together and get a better idea of how these are moving. So just kind of try to keep that in mind. So then I'm going to go through and draw these on my other map real quick. I'll just kind of skip ahead of this for you. And we have our summer solstice and our winter solstice wind current map. So now we need to look at our onshore and offshore winds. So we're going to basically color along the shores with onshore winds versus offshore winds, which will help us when we have to figure out our precipitation and temperature later. And don't let the effects of onshore winds extend inland over tall mountain ranges. So if you want to reference your elevation map here and don't go over probably highlands or over, and the higher the elevation goes, the less that effect is going to extend. So I'll set that up there to kind of reference. You can start with one of these maps, and I'll start with, say, offshore winds. So this will be anywhere that wind is sort of blowing again offshore. And I'll just kind of go around and map that. And not everywhere is going to have strong offshore or onshore winds. If you're not sure about an area, just leave it. Okay, so one thing that I want to mention additionally is that you'll see that for islands, for the most part, they are going to count as having onshore winds because the winds are always going to be blowing from over the ocean. The only cases where islands are not going to have onshore winds is if, like in this case, where I have a lot of air going in this direction where it's all coming from offshore and there's not a lot of space for it to pick up moisture from blowing over the ocean. So I didn't make this island have onshore winds, but basically all of my other ones do because, you know, the air is coming from the water. It's going to have a lot of water in it. Okay, so now that I have my wind currents, I want to just talk about patterns really quick because something you'll notice, and there's a lot of guides out there that are sort of more, you know, in this hemisphere, give it this climate zone, etc., etc. And these sorts of patterns are what those draw on. So for example, you can see in our northern hemisphere, we have a lot of offshore winds, right? But in the summer solstice on this hemisphere, we see that we have a lot more onshore winds in these areas, which gives it a much more of a seasonal sort of weather effect when it comes to like precipitation and temperature, which we'll see once we get to mapping those out. And also in the southern hemisphere, we're actually going to see a little bit less of this effect based off where it is. But that's also, this is right around this band. There isn't a lot of large continents here. You do get a lot of low pressure here, which means there's going to be a lot of onshore winds. So you can sort of like pick up on patterns, but again, this isn't exact, like where these areas are precisely, like this has offshore winds in both seasons, right? So that's going to be a lot drier of an area. It's going to have a lot more consistent temperatures versus these areas, which are going to have more seasonal differences because of how that, you know, wind is circulating and how the temperatures and precipitation in that wind is going to get affected by, you know, all the things. We'll get into that in the next one. But this is going to result in a more nuanced distribution of your like climate regions. So if you look at a lot of the guides where it's just like, oh, in, you know, around this latitude, give it this climate zone in this area, right? You're not going to see as much granularity in those climate zones, whereas we will get a lot more granular because we're getting a lot more specific, right? And to some extent, does this really matter? This is always a question, but I like to think that it really does matter because, for example, if you had a civilization here, right, you are not going to have a lot of seasonal effects. You're not going to have a ton of maritime effects. So this climate would be entirely different. And having different like civilizations and societies closer together geographically and having them be experiencing more severe climate differences is going to have a big impact on those people. If everyone in like this entire continent almost, there's basically a certain type of climate that's on the shores and a certain type in the middle, like that really only gives you two options. You're not going to have a lot of ability to pull inspiration from the climate itself because it's just going to be the same in a lot of areas. So this is one of the reasons I like doing it like this, and this again is not perfect. Wind currents is probably the hardest part of this because you have to kind of figure out how to balance, you know, these effects from the high pressure zones, low pressure zones, and the, you know, normal wind currents with the wind belt. So it's hard, but I would just, you know, really recommend trying to really extend those onshore winds really far where it makes sense to. Like you can see, I have these going in really far in. Offshore winds won't really have as much of an effect and as big of an area, but, you know, just kind of keep this all into account and, yeah. So at this point, our next step is going to be mapping out ocean circulation, and then once we have that, we can go into doing temperature and precipitation, and then it's climate. So I'm really excited about that. So now that we have mapped our air circulation, our wind currents, our high and low pressure areas, we are starting to get a really good picture of our world. The next step is going to be ocean circulation. And after that, we'll be ready to start making our climate maps. Like all of these parts, I have a lot more resources linked in the blog posts that are kind of corresponding to this part in the Worldbuilding Guide series. And so if you want to kind of do further research, I definitely suggest you check that out. They're all great articles and resources if you want to look into this further, and you can also just in general do your own research. But I'm going to get ready for the next step, and I will see you next time.